Hello. So in this video for Monday, April 20th, 2020, which I'm making on a day that is snowing outside, which is totally weird because it's April, but it is northwestern Pennsylvania. Anyway, so in this video, we are going to review rates of reactions and consider how changing the temperature changes the rate of the reaction. So a little bit of a review into kinetics from last semester so that we can think about what happens with temperature, the one question we didn't get to in Chem 120. So first, let's review some kinetics. So we want to think about what do we mean when we talk about the rate of reaction or reaction rate. Right? So reaction rate is the change in concentration of one of the reactants or products divided by the time interval over which it occurs. Right? So it's a rate just like driving your car, miles per hour, kilometers per second, meters per second. Kinetics is about a rate of change. All right, so if we have a generic reaction, A plus B reactants go to C plus D products, we could think about how the rate of disappearance of reactant A changes. Right? How does A, final minus initial, change over a time period, delta T? So we can make those time periods long, or we can make them instantaneous, right, with dA dt. So we can think about how it disappears. So we multiply by a negative sign so that our rate is a positive quantity. So this is what we did last semester with our blue versus bleach, blue plus blue food dye and bleach reaction. The blue disappeared. We watched the blue disappear. There are other things where we might care about the appearance of something. So the appearance of a product, how does it change over time? The rate of appearance of product of C. And since we're in the midst of this COVID-19 pandemic, we are looking a lot at rates of change. How does the disease spread? What is the rate of change over time, and how can we slow down that rate? More on that in a moment. Right? So note that for chemical reactions, the rate depends on stoichiometry. The overall rate depends on these coefficients, A, B, C, and D, if we're relating one to the other. So let's look at our actual reaction, the synthesis of gas phase water from hydrogen gas and oxygen gas. Note that hydrogen gas is going to disappear twice as fast as oxygen disappears as they come together to make water. Right? So the rate of change of hydrogen is faster, 2 times faster than the rate of change of oxygen. So if we want to talk about the overall rate of this reaction, we would say that the rate of this reaction is equal to -1/2 the rate of change of hydrogen with respect to time, which would be equal to the negative of the rate of change of oxygen with respect to time. Since this rate happens twice as fast as this rate, these two will be equal. More generally, we can look at the overall kind of generic reaction and say that the rate of change for this overall reaction is going to be -1/A, the first coefficient, times the change in A with time, or -1/B, second coefficient, times the rate of change of B with respect to time. And that would be equal to the +1/C times the change of concentration of C with respect to time, which would be equal to 1/D times the change of concentration of D with respect to time. So this is how we can represent the rate of reaction. How is it changing? How is our concentration changing with time? The other thing we want to review really briefly here is to think about what factors are influencing how fast a reaction happens, or the reaction rate of reaction. So just for review, the chemical nature influences how fast a reaction happens, right? Different molecules react at different rates depending on how accessible they are and how they can connect with each other. The concentration has an influence, right? Molecules need to connect with each other in order to react. They need to collide. So if we increase the number of molecules, we will increase the probability of them finding each other and reacting. So concentration increases reaction rate. The physical state is also important. The molecules need to mix to collide. So if we're thinking about a reaction that involves a surface or a solid and a gas, they need to come into contact with each other. And finally, what we'll focus on later in this video is temperature. Molecules have to collide with sufficient energy to react. So temperature has a big influence on the rates of reactions. A little bit more review about integrated rate laws and how do we know the order of reaction. Here's where I'd really like to just leave this question hanging and ask you all, how do we know this? Can we just look at a reaction and know what the order is? If it's first order or 0th order or second order or half order? And you would all shout out, no, we need data. The only way we can know the order of a reaction is to analyze the data of that reaction. Conveniently, your textbook has this nice decision tree for us to think about how we can decide the order of reaction, right? So we need a plot of data. How is concentration changing with time? That's how we can tell the order of reaction. So our first question is the concentration versus time plot linear? If yes, it's a 0th order reaction. So that tells us that the rate law would be equal to the rate law is equal to the rate constant. It does not depend on concentration at all. The rate is constant over time and depends only on the rate constant, not the overall concentration. The integrated rate law, so this is the linear form of this, so we see that we've got concentration as a function of time is a line. Concentration as a function of time is a line. The y-intercept is the initial concentration, x naught, and the slope of this line would be negative k, where k is our rate constant, lowercase k, which I'm going to use blue throughout this video to help us keep track of that k as opposed to our rate constant, capital K, that we talked about in the last video. We can also think about the half-life. How long does it take for half of our material to disappear? For a 0th order reaction, that depends on the initial concentration and the rate constant. So if we're looking at concentration versus time and it's not linear, the answer to this first question is no. For example, it looks like this, not linear. Then our first thing to do is to plot the natural log of the concentration x as a function of time, right? We want to see if it fits an exponential curve. Does this curve, is it an exponential curve? So this is exponential decay. Right now we're talking a lot about exponential increases in the number of COVID-19 cases. So there's been a lot of discussion of exponential functions in the news in the last month or so. So if we're plotting the natural log of the concentration as a function of time and it is linear, the answer is yes, then that means we have a first order reaction. And the rate law would be the rate equals the rate constant k times the concentration to the first power, which we usually leave off. Right? The integrated rate law in its linear form is that the natural log of concentration as a function of time, right? So this is my y, time is still my x. The y-intercept is equal to the natural log of the initial concentration x naught. And again, the slope is equal to the negative of the rate constant k. The half-life, t1 half, is equal to the natural log of 2 divided by the rate constant k for a first order reaction. If this was not linear, and the answer is no, then we try to see if it's a second order reaction, and we try to fit the data, the reciprocal of the concentration, 1 over the concentration as a function of time. Is that linear? If that's linear, then it's second order. And the rate depends on the rate constant times the concentration to the second power. So that's our rate law. So if we're thinking about how we think about that another way, if we double the concentration in a first order reaction, it doubles the rate. If we double the concentration in a 0th order reaction, it has no effect on the rate. If we double the concentration in a second order reaction, it will quadruple the rate because there is a second order dependence of the concentration on the rate of reaction. The linear form of the integrated rate law is 1 over the concentration is equal to K times T, right? So our slope is then equal to the rate constant K, and our intercept is equal to 1 over the initial concentration X naught. This half-life would be equal to 1 over K times the initial concentration for a second order rate law. So again, thinking through how do we know the order of a reaction, we can think about how does changing the concentration influence the rate. If it doubles, it's a first order reaction. If it quadruples the rate, when we double the concentration, it's a second order reaction. But the main way we do that is to plot the data, right? Concentration versus time, if it's linear, 0th order. Natural log of concentration versus time, if that's linear, it's first order. 1 over concentration versus time, if that's linear, it's second order. So the only way we know the order of a reaction or how concentration influences the rate of reaction is to collect data, plot that data, analyze these different manipulations of that data to determine whether or not the reaction is 0th, first, or second order. Okay, so now we want to think about temperature. How does the reaction rate depend on temperature? So qualitatively, it's kind of our observation that most reactions go faster when temperature increases. Right? It's why we cook our food, because it breaks down cell walls and decomposes the proteins, makes them easier to digest. It's also why we refrigerate food, because we don't want it to decompose. So getting it cold slows that reaction down. So qualitatively, we know this. Quantitatively, we can go back in history a little bit. It was first identified by a Swedish chemist named Savant Arrhenius in the late 19th century. So then we now call this relationship the Arrhenius equation. So he found that if you plot the natural log of the rate constant, K, as a function of reciprocal temperature in Kelvin, you will get a straight line. So how does a reaction rate depend on temperature? All of that information is carried in the value for the rate constant K. Rate constant K changes with temperature, and it changes in a linear way, or actually an exponential way, right? The natural log of the rate constant K as a function of temperature gives us this Arrhenius line. So let's put in some factors, Arrhenius factors, these are called, where we can think about the natural log of K, rate constant, where our intercept is equal to the natural log of A and our slope is equal to the negative EA over R, where A is called the frequency factor or the pre-exponential factor, EA is called the activation energy, and R is our universal gas constant, 8.314 joules per mole Kelvin. So we can think about it in this Arrhenius equation linear way, or we can think about how does temperature influence the value of K in this exponential way, right? That K is equal to A times the exponential of EA over RT. So if we increase temperature, K becomes larger. It increases the rate constant of K. So these parameters, frequency factor and activation energy, how might we determine them? We're staring at this graph, we can graph the data, right? Like most things in kinetics, how we get answers is to graph data and extract information from those graphs. So if we collect rate constants, how does K change at different temperatures? So thinking about, well, how could we find the rate constant? Oh yeah, we plot it, right? So for example, it's first order, we plot the natural log of the concentration as a function of time, and then the slope of our line is equal to the negative of the rate constant. So we could do that for a whole bunch of different temperatures. And then we would have a plot like this. From the slope, right, we can get the activation energy. From the intercept, we could get the pre-exponential or frequency factor, A. So we determine all of these information, A in EA, from graphing the data. Let's talk for a moment a little bit more about these parameters. What do they tell us about a reaction? So that we will talk more about the theories in the next video. So A, our pre-exponential or frequency factor, is the term that tells us how the molecules collide and the probability of an orientation such that they can react with each other. So you can imagine two balls coming together if molecules were just balls, but they're not just balls, right? So they have a shape, they have an orientation. If we change that orientation, they could collide with each other, but they're not orientated such that they can react with each other, or they are orientated such that they can react with each other. This term A tells us about how that works. The second Arrhenius parameter is activation energy, and this term deals with whether or not the molecule has sufficient energy to react. Right? The activation energy tells us how much energy it takes to react. Both of these parameters, as we just saw, are determined by experiment, right? We need to do the experiment, we need to make the plot, and then from the plot we can get the values for A and EA. And generally they are nearly temperature independent and depend on only the reactions being investigated. So if we look carefully at the dependence of the rate constant K on temperature for just two reactions, one that has a low activation energy and one that has a high activation energy, we note that the one with the higher activation energy has a stronger dependence on temperature than the one with a low activation energy. What we can do from that Arrhenius equation is put two of them together to get another Van Hoff relationship. How does changing temperature change the rate constant K? So in this case, we see that the natural log of K1 over K2 is equal to the activation energy EA divided by R times the quantity of 1 over the reciprocal T2 temperature minus the reciprocal T1 temperature. So this means that if we increase temperature, we will increase the rate constant, or the rate constant increases with increasing temperatures. And that rate constant is larger when the activation energy is larger. So let's think about how we could use this in an example question. In this example, the hydrolysis of sucrose is part of the digestive process. To investigate how strongly the rate depends on our body temperature, calculate the rate constant for the hydrolysis of sucrose at 35 degrees Celsius, given that the rate constant K is equal to 1.0 milliliters per mole per second at 37 degrees Celsius, which happens to be normal body temperature, and that the activation energy of this reaction is 108 kilojoules per mole. So what we're doing is using this Van Hoff reaction to predict the rate constant at one temperature, given that we know what the rate constant is at a different temperature. So if we know, for example, K2, let's make that our K, so that our T2 is then 37 degrees, then our T1 can be 35 degrees. So let's just focus on this half of the equation. So our activation energy is 108 kilojoules per mole. R is 8.314 joules per mole Kelvin, or 8.314 times 10 to the negative third kilojoules per Kelvin mole. We want to make sure our units cancel out here. So that also means always our temperatures are always in Kelvin. So our higher temperature here, 37 degrees or 310 Kelvin, minus our lower temperature, T1 of 308 Kelvin. So if we multiply all that out, we'll get negative 0.27. So my natural log of K1 over K2 is equal to negative 0.27. So if I want to solve for the value of K1, I'm going to have to exponentiate both sides of that equation. So I get K1 over K2 is equal to the exponential of negative 0.27. So K2, remember, goes with T2, so that is our higher temperature. So this K2 is 1.0 milliliters per mole second times the exponential of negative 0.27. So K1, the rate constant at a lower temperature, is 0.76 milliliters per mole per second, compared to our rate constant at the higher temperature, which is slightly higher. And that makes sense, right? That at a lower temperature, the hydrolysis of the sucrose would be slower than at a higher temperature. So for more practice with these concepts of how temperature influences the rate of reaction, please complete activity 26. This is the last activity of the semester for practice with these concepts. It will be a blank copy will be available on Sakai, and the answers will be entered into the Sakai exams and activities as they have been for the last month or so. And that is it.